Thank you. Let's start, Jose Maria.
Okay, thank you. Welcome everybody, and thank you for coming here today. I appreciate you took the time, especially Gabriel, Ruben, and Jesus. Thank you. I want to start by talking of what 3D perception is. It consists on understanding the 3D structure around the images, and there's many problems grouped within the term perception, and those include object recognition or object detection, reconstructing a 3D representation of the scene, to even estimating the ego motion of the camera itself. Sometimes we'll have to solve this problem by using multiple views of the scene, and sometimes we'll have to deal with the fact that we have only one single image. Understanding the 3D is a fundamental key for many different applications, including some of them that are very trendy right now, like self-driving, that cars that are fully self-driving will need to not only recognize another car or pedestrian, but also estimate the distance to them in order to maintain safe velocity all the time. Also, AR, VR headset will need to track the position of our head as it moves in order to maintain the virtual simulation moving accordingly, so that it feels comfortable and doesn't make us feel dizzy. There is particularly two perception problems that are really interesting, and those are the estimation or tracking of the camera pose and building a 3D representation of the scene. These two problems both benefit very much of having the other one solved, meaning, for example, it's much easier to track our position if we have already a map built of the scene. However, what is really interesting is to tackle these two problems at the same time. This problem is referred as simultaneous localization and mapping, or SLAM, and we refer to it as visual SLAM when we use only visual sensors such as cameras. The general visual SLAM is has been addressed successfully, and it works pretty well under the right conditions. However, there are certain situations in which still it presents some open challenges. I want to introduce now some of these open challenges by first introducing the nature of the error in a multi-view mapping for traditional algorithms. And the reconstruction is done for a point by intersecting rays among different camera viewpoints. And the matching of this point may have error in the image, and if we propagate this error, that's the nature of our 3D estimation. This error increases in two particular situations, and these are, for example, in low texture surfaces, such as a plain wall, where the matching error increases in the image, and so does the 3D reconstruction in the 3D space. And the second one is when the camera moves very little, the angle between the rays decreases, and that makes increase the uncertainty of our estimation. Being the extreme case of this, the case when the camera does not move at all, and in that case, the rays are parallel and they never intersect. When we are working on applications that are meant to be working long-term, we cannot rely on the appearance of the scene remaining constant. If you look at the example on the top, these two images, they belong to the same scene, but if we will look at local small features, we will see that they have changed in appearance, and it will be very difficult to match ones from one image to the other one. However, we still recognize that's the same scene because we can look at higher level structures such as the statue, the arch, or the fence. If you look at the example below, it's something similar. In this case, the room has changed the furniture or the position of the furniture. And if we will look at small features in the room, they have changed in position or in appearance. So we cannot rely on them. However, if we look at the high level structure of the room, we will see that it's the same room, and we could even recover the pose between the cameras. And the last open challenge I want to talk about is the presence of dynamic elements in the environment. In that case, when traditional algorithms treat points of these elements as static points, that can be really problematic and needs to be dealt with. This thesis took place started at the end of 2016, and we knew about these open challenges, and at that moment, deep learning was growing in popularity, both because of the increase of data and computational power and some breakthroughs over the years. Deep learning leverages from having the vast amount of data and learning statistical models from the patterns it can extract from it. Image science is one of the most advanced on machine learning, and because of that, we thought we propose and our motivation was to bring the synergies of these two models together: traditional multi-view models and deep learning, bringing data-driven designs to traditional models, and bringing also models and understanding from traditional models to deep learning, achieving more general neural networks that generalize better. Today, I'm going to cover our proposals for all these different challenges, and I have structured the presentation first in low level of abstraction, where we estimate low level information for the pixels in the image, and the second part of high level of abstraction where we'll work with high level features. I'm going to start the first part with depth estimation, in which we want to estimate depth value for each pixel on the image. And in this case, we have proposed two works, one for single view depth estimation, which is the extreme case of little motion where the camera hasn't moved at all, and the second one for multi-view depth estimation. When we work on single view depth estimation, we cannot rely on multi-view geometry anymore because the camera hasn't moved. So what the community has done over the years is apply learning the relationship between patterns in the image and their distance to the camera. In the learning community, there has been proposals of deep learning since 2014, and as I mentioned, deep learning benefits for having a vast amount of data. However, the way we are doing the validations still it is always the same. We take one data set, we train on this data set, and validate on this data set. And again, we take another data set and train and test. And what we'll like to do is really be able to leverage from all this amount, all these data sets, all this data, and use it to create models that generalize better. However, that cannot be done carefully because all these data sets have been recorded with different cameras. And I'm going to motivate now with the following example why this is important for a task such as depth estimation. Here in this example, I show you a portrait of this man taken from different positions and with different cameras, changing the focal length. And you'll see, if you look at the examples, at the pictures in the 2 rows below, here, you will see that the feature face, it's always at the same position and it has always the same size. So if we were to train a neural network saying all the time that this face is at a different depth, it will be really complicated to make it converge. And I'm going to show now the other side of the coin, in which all these images have been taken from the exact same spot, but they have been taken with different changing camera parameters, such as focal length or sensor size or principal point. So in this case, the lighthouse that you see in the image is always at the same distance. However, the pattern in the image is changing. So what we want to bring is the camera model to neural networks. And for that, we propose a convolution operation that we name CamComs because we want it to be shift and space invariant. In order to bring the camera model to the operation of convolution, we need to add pixel-wise information of the camera model. And for that, we include the center coordinate maps and the field of view maps. The center coordinates give information about the principal point and the sensor size. And the field of view map gives information about the context that the camera is capturing and the focal length. You can see here below in the example of the lighthouse how these maps change depending on which parameter of the camera is changing. What we do is we concatenate these maps to the previous layer feature maps, and we apply convolution normally. And the way we add this into a convolutional neural network is in the connections between the encoder and decoder. In a unit architecture, it will go on all the skip connections. And the reason we do it like this is because first, in our experiments, it proved enough to map from uncalibrated RGB features to calibrated depth features that can be decoded into a depth image. And second, because this way we can still use pre-training for the encoder on on calibrated data or on tasks that do not require calibration, such as object recognition. Validating this work was really challenging because we cannot simply take two data sets from the ones that I showed at the beginning, because although they have been recorded with different cameras, they also have different domain. And in that case, if we were to see some drop of performance, we will never know if that's because of the change in the domain or because of the change in the camera. So in order to validate the generalization across different cameras, we use the 2D, 3D Stanford semantics dataset that has been recorded with omnidirectional cameras and synthetically simulate different camera models that we can evaluate and test in. We also perform a threefold cross-validation in order to ensure the robustness and fairness of our results. And here I showed you an illustration on how we create synthetically different camera models, and you can see also how the maps, the center coordinates, and the field of view maps change depending on the camera calibration matrix. So the results for this experiment are really extent, and I'm going to try to keep it as brief as possible here with this summarized table. First, I want to introduce the columns in the table. The first one, it tells the set of cameras that are being used in each moment for the test. The first part, it refers to the sensor size, that is S1, explained in the table below. And the second one, it refers to the focal length we are using. In this case, the U refers to a randomly sample from a uniform distribution from 72 to 128. The second column, it tells the same thing, but for the training set. When the row is in red, it means that the network is being trained on the same set of cameras as it's being tested in this experiment. And the network that says CamComs is the only one that has CamComs on it. And in that case, it's been trained, as it said in the line below the table, on sensor sizes S1 and 2 and uniform focal length from 72 to 128. I want you to look first at the two first experiments. And in this case, we are comparing CamComs that has been trained with two sensor sizes with the two baseline on each sensor size separately. And in this case, this was the only network that having been trained on more than one sensor size, was able to achieve similar performance or even outperform, in this case, the baseline that has been trained on the same camera model. The second experiment, it's a bit more tricky. In this case, we changed the sensor size to a different one. And I want you to look here at the last two rows. In this case, these networks have been trained with exact same data, sensor sizes 1 and 2. The difference is that one has CamComs on it and the other one doesn't. And you can see the performance is much better in the CamComs one. But not only that, it's also able, in this case, not having trained on that sensor size, to achieve better performance than the baseline in red. And last, the last experiment is also the most revealing. In this case, we are testing on a completely different sensor size. This is the most different one, and a focal length that is out of the distribution of training. And not only that, it's just one sensor size and one focal length in this case. And if you again look at the last two rows of the table, you'll see that these two networks that have been trained on the same data, the one with CamComs maintain performance, even though the camera is totally different, and the one without CamComs drops performance by a lot. In this case, if you compare with the baseline in red, you'll see that the performance on CamComs, even if it gets close, is not as good. And our conclusion here is that in this case, this network is training for one camera model only, so it's much easier to overfit this camera model and then achieve better performance. And here you can see some qualitative examples, and if you look at some parts of the image, the network with CamComs against the network without CamComs, it also not only gets better at scale, but also better details in many parts of the image. And now I move to the last experiment of this work, which is kind of like the motivation of it, in which we want to train with multiple data sets. So we picked 4 data sets, 2 outdoors, Kitty and Mega Depth, and Scanet and Sun 3D for indoor. And we train in all of them. And now I want to show you some of the of the results. On the left, you can see qualitative results on Kitty, on Mega depth as well, and on the right, an evaluation and comparison on the NYU dataset as part of the indoor domain, which is a dataset that we haven't trained on. So it's a completely new dataset for us, for our network. And we are comparing here with the state of the art in this dataset at the moment of this publication. I want you to look to the box plot below. Here we have evaluated with different camera models created the same way that I showed you before. And if you look at the distribution, the minimum point of the error that the state of the art achieves, it's lower than the distribution of our error. And this is because we have included the camera model, the original camera model, which they use for training, into the test set. However, if you look at the overall distribution, you'll see that our performance is much better. And this matches the result that we got from the previous experiment. Now, I'm going to move to the second work on depth estimation, which is the multi-view depth estimation. Here, we're going to combine traditional models with single-view depth estimation from deep learning. So first of all, I'm going to do a brief comparison between them. On the one side, the multi-view depth by traditional methods is very accurate on high gradient pixels and on high parallax motion. However, it's not so accurate when it has low gradient and low parallax. On the other side, deep learning is fairly accurate for all pixels, and it can work on single view image, so it doesn't need motion. We can approximate the scale with deep learning. And for the last part, I want to illustrate with these images. Here, the error in the multi-view on the left, you can see that the error on these points depends on geometry, and it doesn't matter if one of these points belongs to a chair and the other one to a table, or they both belong to the same object. The error isn't correlated. And on the other side, the error of a single view depth estimation by a network, I'm using this example to illustrate where I saw the RGB image and an error image where the dark blue is lower error and the light blue is higher error. And if you look at the error in this wall, it's practically constant in the sense that the whole wall has the same error, which means that it's been successfully estimated as a plane. However, the error is not coherent with the rest of the walls. And so it's locally, it depends on the image content and it's locally correlated. And if you look just at the corner, at the left and at the right of this corner, the geometry is the same and still the errors are different. So the nature of the errors of these two methods is different. So in this work, we want to leverage from that and try to combine the strengths on these two methods, having a dense depth estimation that leverages from motion and learning. And for this, we propose the following pipeline. We part from an RGB sequence, and we want to estimate dense depth estimation for a reference frame, for which we predict a single view depth estimation with a single view neural network and multi-view semi-dense depth estimation. And what we propose is depth fusion to combine both of them and achieve a better result. I'm gonna introduce now this fusion as that we present as a weight average. And for this case, I want to illustrate it with this case where we have a set of points for which we have a depth estimation from the multi-view that this set of points is called omega, and we have a dense estimation from the neural network from the single view. So if we want to estimate the depth for a pixel ij, what we do is we take points from the multi-view, we apply the gradient from the single view, and we average them. Remember that I just told you that the error in the single view image is locally correlated. So what we will want is that points that belong to the same local area influence point on this local area and not points outside of this local area. So for that, we use these weights. These weights are the product of 4 factors. The first one, it depends on the distance in pixels in the image, having 1 point more influence on the pixels that are near him. The second one depends on the estimation by the network. We look at the single view depth estimation, and if it has similar depth gradients, 2 points are more likely to be part of the same local structure. And last, the second one, look again at this at the prediction by the network, and if 2 points belong to the same plane, they're more likely to be part of the same local structure again. When we multiply all of them, we get something like this. In this case, you can see how this point has bigger influence on the points that are immediately close to it, but it spreads its influence all over the table, but it gets cut right at the edge. When we add all these influence weights and we normalize them, we get something like this. In this example, I have colored the point depending on which local structure they belong to, so that it's easier to visualize. And here, I want you to look at the example that is being zoomed here in the corner between the wall and the trash can. And here, the floor points have a really close blue point and red point. However, if you look at the influence that it's getting, it's coming mostly from the points in the floor, even though they are far away. When we apply this fusion, we saw that evaluating on different sequences of 2 different data sets, we saw that the performance compared to the single view depth estimation was much better. And you can see on these qualitative examples how, for example, in the bathroom that I just showed you, the wall of the single view depth estimation in our estimation is being pushed away, and now it matches the ground truth depth. You can also look here how the chair in the living room now is being brought up, and you can perceive it much better in the depth image. And last, in the office, you can see how the wall at the end of the office is being pushed away, but maintaining the chair that that is there in the image, in the ground truth. So here I get to the end of this first part of low level of abstraction, and I want to conclude by saying that CAM-COMS is the first approach that includes the camera intrinsic parameters into a convolutional neural network to achieve generalization across different cameras and data sets. We perform an extensive study to analyze how much improved we can get from it, and we are able to recover real scale on different data sets. We published this work on CVPR 2019, and we have made our code public in GitHub for TensorFlow. And I'm really happy to say that the community has implemented CAM-COMS for PyTorch as well. And I'm really excited to see that some recent work has used CAM-COMS on self-supervised monocular depth, proving that it can also work on that type of training, and also for a scene flow. Recently, Mapillary has presented a huge depth data set that includes different camera models and many different parts of the world. And in their work, they also the only network they compared with was using CAM-COMS, because it was the only one capable of training and recovering real scale across all different cameras. And last, the single view multi-view depth fusion is one of the first approaches that combines deep learning and geometry, proving that traditional multi-view models can and deep learning can be complementary approaches. We published this work in RAL and IRIS in 2017, and parallel to this work, there were also some proposals proving the same idea. On the one side, CNN SLAM combined single view depth estimation with a semi-dense SLAM system. DeepTam more recently proposed an approach that combines multi-view images just by learning. And in Deep Fusion, they propose a work that also combines gradients from single view depth estimation and points from multi-view depth estimation, but with traditional models. Now, I'm going to move to the second part of the presentation, the higher level of abstraction. I'm going to start with condition-invariant place recognition. In this case, we want to tell when we revisit a place, which place was it, and we want to do it even though the conditions and the appearance of this environment have changed over time. Like you can see in this example with different seasons. And this is really important for many applications. For example, it's very important for self-driving, where the conditions because of weather or light changes may change, and we need to be able to figure out that we are on the same place. The problem that I'm going to present goes like this. We have a database of previously visited places, and when we have a query of a new place, we need to find the match in that database of the same place. The way we propose to do it is to use the internal representation of neural networks. We know that deep belief neural networks get enhanced and compressed representation of our data, and what we want to do is leverage from these codes and make being the input, the images recorded in a place, making the code of the neural network be similar for images that have been taken on the same place and different for images that have been taken on different places. And for the first time, we proposed three architectures for deep learning that leverage from sequentiality of data to generate the descriptors. For that, we propose three architectures, as I said, and one is descriptor grouping, in which we concatenate descriptors done by single view networks. Descriptor fusion, where we combine with a fully connected layer the features extracted with CNNs, and recurrent descriptors, where the descriptors updates its value as more images come. The way we train this is in a Siamese manner. We produce the descriptor output for first an anchor and a positive example of images taken in the same place, and a negative example of images taken in a random different place. And we apply a triplet loss that will try to bring descriptors of the same place together and descriptors of different places far apart. And to visualize this, instead of using, I'm gonna show you an example, but instead of using descriptors of 128 elements, I'm gonna use a descriptor of 2 so that we can visualize it for the example of MNIST for 10 classes. And you'll see that in the initial case, all the descriptors here on the left are all mixed together. And as it goes to training, you can see how these points separate and they cluster with points of the same class to have final representation where they are all separated. So if we will now query this system with an image and we get a descriptor of it, it will be very likely this descriptor will be near points of the same class. To evaluate our models, we propose to use the Norland dataset. This is a dataset of recorded with a train between two cities of Norway, and this dataset has been recorded in 4 seasons of the year. It has GPS data, so it's fairly easy to tell when 2 images are part of the same place, even if they were recorded at different times. And however, we didn't find in the community an agreement on which partitions of data to use, because there's not in the official data set. And for that, we propose the following partitions. We propose to use 3 different test sets on 3 different parts of the sequence so that we have geographically 3 different places and more diversity. And the rest is for training, but we drop frames in between the train set and the test set so that there's no intersection of views of images. In total, the data set has 30,000 images, being the 15% of it for test. Here I show you a comparison of all of our multi-view approaches for descriptors and all the state-of-the-art previous to our publication. And here you can see that the performance of our methods, both the accuracy for winter versus summer and summer versus winter. So we are querying with the one on the left and finding the best match on the one on the right, and showing the percentage of times that we get the correct match. And you can see that the performance of our descriptors, it's much higher in comparison with single image, proving that the idea of leveraging from sequential data helps. We also had a comparison with our single view neural network to that it's been trained the same way, so that we have a fair conclusion. However, if you look at this, you will see that the grouping algorithm, the more naive, it's the one that gets the best performance. And here we thought that concatenating descriptors could leverage from the fact that these sequences are very aligned and they happen through the same places at the same time. So for to compare the robustness of our different approaches, we propose 2 extra experiments. And these are reverse gear, in which the query sequence only on test is run as reversed. So like if the train was going backwards, And the second one is random speed, where we'll drop certain frames randomly to simulate different speeds on the trajectory. And here, if you look at the last 3 rows of the table, you'll see that of our methods, grouping drops the most performance of them, because, as I said, it's leveraging from this sequentiality and this alignment of the sequences. And on the other side, both fusion and recurrent prove to be more robust, especially the recurrent one, which is the one that shows the lowest standard deviation. Here we have also compared with SexLAM. This comparison needs to be taken carefully because SexLAM is not using multi-view descriptors, but single-view descriptors, and then is using multi-view matching algorithm. And in this case, using the same number of frames, it occurs something similar to our grouping because they also leverage from the sequences being aligned. Here I show you some qualitative examples. On the top, you can see the query sequence on fall, and on the bottom, you can see the retrieve places for all different seasons. If you look at the end of the winter sequence, you'll see that the camera gets foggy, and the network is still to retrieve good descriptors that we can use to recover a good match. And last, I want to show you some failure cases for the winter use as a query. Here you will see now in red frame some cases in which the recovery is not done correctly because we are recovering images that are too far from the query example. So to conclude this part, this is the first approach that we know to use multiple images to generate descriptors for place recognition with deep learning. We proved that it shows better performance and that the robustness depends on the approach that we use. We published this work in several workshops, and the code and dataset is made available on the website of the project. I'm really happy and excited to see that that recently there was a new proposal of a dataset, a huge dataset, and they validate our idea, proving that sequentiality can be used to generate better descriptors. I move now to the second part of the second work on this, the higher level of abstraction, to layout estimation. The layout is the layout of a room is the higher level of abstraction of it, and is taking now more and more attention because of the many applications it's useful for, such as indoor robot navigation, AR or VR, or even real estate. But what it is a room layout exactly? A room layout is the main structure of the room, meaning the walls, the ceiling, and floor. It can be estimated in 2D and 3D up to scale from a single image. And in this work, we choose a corner representation to represent the layout. Here I show you 2 seminal works, both with perspective and panoramic images. And they both show impressive results. However, there's a common assumption in both of them, and it's that the rooms have 4 walls and 4 walls only. While this is something understandable for perspective images because they don't get to see more than 2 walls normally, we think that this oversimplification should be break with panoramic images, and that motivated us to use spherical images for this task. So the challenges that we faced here is first that we want to estimate 3D structure from a single monocular image. We want to deal with the spherical image distortions with a high level of occlusion and clutter, and overcome the 4-wall simplification, also reduce computational times. For that, we propose a fully convolutional neural network that will produce 2 probability maps, one for corners and one for edges. Training in this joint learning task proved to work better and converge faster because these are 2 very related tasks. And this output representation does not restrict our output to have 4 walls, but could potentially have any number. As I mentioned, we are going to work with the spherical images. And for the spherical image, we choose the equirectangular projection that maps directly meridians and parallels to vertical and horizontal lines that are codistants in the plane of the image. And So we have a direct mapping from the sphere surface to the image. However, this mapping does not come without a cost, and is that it produces distortion. These distortions are more pronounced near the poles because we are stretching the parallels to match the image width. And being in the top row and the bottom row, the stream case that actually are mapped from only one point of the sphere. We have the problem that traditional convolutional neural networks do not deal with this type of distortion, so and they're going to ignore it. So the feature they're going to learn have distortion patterns. So for to avoid, and not only that, a spherical image, in the spherical images, the left and the right are at the same spot in reality, and normally standard convolutions are used with zero padding, so they're not going to understand the continuity of the scene. I have shown you, I'm showing you for this image and below an example where I have concatenated these two images, and you'll see that the corners and the left and the right are actually the same. So we will not want this corner to be detected twice, but just one. For this, the community has proposed rectangular kernels, and although they prove to work better, they're not dealing with the problem of distortion, and they're not understanding the continuity of the scene. So for this, we propose rectangular convolutions, and then we define a spherical kernel as by its relation between the resolution and the angular size. We imagine a 3x3 kernel tangent to the surface of the sphere, and that it touches right in the center. We can define then its point in the kernel by its ray from the center of the sphere, and we can convolve it through the sphere by normalizing the rays and rotating it using the spherical angles. We can map from these points on the surface to the rectangular projection using the mapping that I mentioned before. To implement this, we leverage from a previous idea, which are the deformable convolutions. And in this case, instead of learning the deformation, what we will do is we will bring the distortion model from a rectangular projection. And with this, we get a convolution that first is distortion aware and deformation invariant, as you can see on the example on the left. And second, it doesn't need padding anymore. If you look at the example on the right, you'll see how it deformed its shape, now being on the right part of the image, and the right points of the kernel, they deform to the left side of the image, and understanding the continuity of the scene. And last, we can use pre-training on standard data by simply removing the offsets in the deformation, so we can leverage from all the data that is being recorded with perspective images on other tasks. And the last step of our proposal is to go from the 2D representation of corners by your network to a 3D model of the room. In this case, we reduce the assumptions that are normally done to only two. One is that the ceiling plane and the floor plane are parallel, and they are both oriented upright, and that the camera is at a certain height. This height is irrelevant because we're doing an estimation up to scale, so it is just a constant. And the way we do it is by using directly the 3D ray representation of the kernels, the corners that go from the center of the sphere to the output by your network. And we intersect these rays with the plane at a distance h, and then we find the corresponding height for the ceiling so that the corners are right on top and they satisfy the rate equations. We compare our proposal with different approaches, and we also train our proposals with a standard and with the rectangular convolutions to see the improvement of the same neural network using ones and the others. And we see that our network, it performs better in all the cases, and not only that, it's also much faster. And if you look, if you compare the one with a standard convolution to an equirectangular convolution in the last two rows, you'll see that equirectangular convolutions work better. However, standard convolutions do not work so bad. And looking at this, we saw that all the images that were recorded in our data sets, both for training and test, were recording at the same height all the time. And the effect that it has is that the distortions created by the projections are very repetitive. And we thought that standard convolutions could be leveraging from these patterns that are generated to estimate, to learn the layout. But that conditions will change if the camera moves. So we apply a new experiment to measure the robustness of both approaches by moving the camera and rotating, such as if a drone will hold the camera or a person will have it in their hand. And here we saw that the approach with EquiComms is much more robust and maintains a better performance in all the cases. Here you can see some qualitative examples. On pink, you can see our prediction, and on purple, you can see the ground truth. It's hard to distinguish because they are one on top of each other, but you will see on some points where you can see they differ a little bit. And here are some qualitative examples of the 3D layouts. And you can see how we have recovered rooms of not only 4 walls, but also this L shape here and here. So we proposed an end-to-end approach that proved to be much more accurate and faster than the state-of-the-art approaches. We contributed with EquiComms, proposing a distortion-aware convolution that can be used for images with distortion patterns and be aware of it. And we are able to recover the real shape of the room. This work has been published in 2 workshops, one in SCCB and CVPR, and also it's been published in RAL and ICRA in 2020. Our code is available on the website of GitHub and the website of our project for TensorFlow. And I'm really happy to say that it's being added to TensorFlow add-ons, and that the community has also implemented EquiComms for PyTorch. And last, I'm really excited to see that our colleagues have also tested EquiComms on different tasks, also for rectangular images, and it proved also to work better for 3D object recognition. And now the last part of this thesis, the last proposal, is a SLAM on dynamic environments. Here we want to estimate the camera ego motion and build a map of the scene on the presence of dynamic elements. And I'm going to illustrate first the problem with a SLAM system failing in the presence of dynamic elements, because it's using points on a dynamic object as if they were static. Here, the camera is still all the time. However, because it's using points on the person, and the person now is going to move to the right, the estimation here of the pose is moving, as you can see. So this is something that we will want to avoid. And to do that, we're going to bring learning from data, and we're going to see how we can detect potentially dynamic classes on the image in order to ignore the points on them. So we propose to use a neural network to segment out people, animals, and vehicles. And here, on the example that I showed you previously, you can see how, in this case, we're able to recover where the people are. However, in this case, the book and the chair are moving as well, and we are not detecting them because they are not dynamic objects, but they are movable and they are being moved now. So normally we will not to detect them, but in this case we want to. So for that, we propose a second approach in which we are going to leverage from multiple views, and we're going to force geometry consistency. So if a point changes depth on a small window of time, it will mean that it's potentially a dynamic element or an element that has moved in the scene. So with this, we are able to recover both the people in the foreground and the book and the chair successfully. However, it doesn't work so well for people in the background, as you can see in this example. So it will have to choose. The best idea will be to use a combination of both. However, I haven't mentioned before, but if you think of it, for the multi-view geometry approach, I need the camera poses to select the points. And as I show you in the first example, this is something that is very difficult to get if there is dynamic objects in the scene. So the pipeline we propose to make it work is the following. We have the sequence of frames as an input. We segment the a priori dynamic elements with a neural network, and we run a low-cost tracking. Here we're just tracking the camera. We're not updating the map or applying loop closure. And with these poses, we apply the multi-view geometry approach. We refine our segmentation, and now we run tracking and mapping. We can, with this, achieve a map that does not include dynamic objects, and we can even in-paint the dynamic objects with the previously knowledge of the scene that we had. We have done a stain evaluation. I show you here the RGBD SLAM evaluation on the TOMB dataset, comparing with the state-of-the-art approaches at the moment of publication, showing that it performs better than all of them, and it doesn't fail in any case in any of the sequences we tested on. Here you can see a qualitative example of a map built from a sequence with dynamic objects that does not contain any of these dynamic objects on it. And I'm happy to say that DNSLAM is still one of the state-of-the-art approaches for SLAM and dynamic environments, and we are able to achieve long-term reusable maps and estimate accurate ego motion on the presence of dynamic elements. We have published this work in 2 workshops and in RAL and IRIS in 2018, and the code is made available online, built on top of OrbisLAM on GitHub. I'm excited to see that our colleagues have continued this work, and they have included object tracking into the pipeline, so they don't only estimate the camera pose but also the objects. So if you remember at the beginning of the presentation, I told you that we wanted to face these open challenges by bringing together the synergies of 2 different worlds, traditional multi-view approaches and deep learning, and we have successfully done that for different problems, sometimes bringing models and understanding from traditional models to deep learning, such as we did in CAMCOMS and EkiCOMS, and sometimes bringing data-driven designs to traditional models, such as in depth fusion or on DNSLAM. We have all this work on all those different tasks. It's been published, and the code has been made available online. And during all this time, we found some further questions in some of these problems. And I want to share with you now some of the points that I think that it will be really interesting to work in the future as a follow-up of this. For the first work, CAMCOMS, I think that it will be really interesting to work in an approach that's not required training on multiple cameras to be able to generalize to them, but that can bring the camera model to the operation without having to do this data augmentation. For the depth estimation, I think that adding uncertainty on the fusion will be much better in order to have a better selection of the strengths of both methods. For the place recognition, 2 things that I think that will be really interesting under this change of appearance will be to retrieve the relative pose as well, and exploiting multi-reference and probabilistic methods. Layout recovery, I think one extension of this work will definitely be extending EkiCOMS to work on other operations, such as pooling, for example. And last, for the DNSLAM approach, as I mentioned before, the object tracking is a really nice continuation. And I think that the final deal for this problem is the non-rigid environments, where not only parts of the scenes are moving, but they are also deforming, and you cannot rely on rigidity or aestheticity anymore. Before I finish, I want to say that I'm really happy and proud to have become part of this community with so many amazing people that I've met along the way. I want to say a special thank you to my supervisors, because they've done an amazing job. And also to all my collaborators of the University of Zaragoza, Bourgogne, and my colleagues during my visit research in Freiburg, and also the amazing teams I work with on my 2 internships, one in Facebook in Zurich and one in Apple. So To finish up, I thank you everybody for coming today. I really appreciate it. Thank you.
Okay. Thank you very much, Chema, for your presentation.
Thank you.